Recall that in semiconductors, current consists of electron current and hole current. However, in intrinsic semiconductors, this current is not enough for good conduction. The process of doping increases the number of current carriers in the semiconductors drastically. The first such semiconductor is an N-type. It is created by adding a pentavalent impurity atom to pure silicon in a measured amount. Look at this bonding diagram where antimony is added to silicon. 4 of the 5 valence electrons of antimony form covalent bonds with silicon atoms. The 5th one goes free. This is why the impurity atom is also known as donor atom. Note, no hole is created because this electron was in excess. There are a large number of such electrons, so we call this an N-type semiconductor, where N denotes the negative charge of the electrons. The semiconductor itself is neutral since equal number of protons and electrons exist. Some holes are also created because of thermal energy, that is heat transfer. These holes are accompanied by an electron. However, the addition of pentavalent impurity does not create holes. The holes here are minority carriers, while the electrons freed by doping are majority carriers. In p-type semiconductors, a trivalent impurity is added to increase number of holes. The P denotes the positive charge on these holes. In this figure, boron is added to silicon, and we see that all 3 of its valence electrons form a covalent bond with silicon atoms. An empty space is created which can be filled by an electron, that is, it is a hole. The trivalent atom is hence also known as acceptor atom. This hole is not accompanied by an electron. The majority carriers in a p-type semiconductor are holes. Electrons are created by thermal action and constitute the minority carrier. No electrons are freed here when impurity is added. P-type semiconductor is also neutral since number of electrons and protons are equal.